We have covered append and its cost. Now we turn to the other three jobs. Let's see how fast we can read a value and how fast we can insert or delete inside the array. Reading and overwriting an element is the same address math from Chapter 2. The only change is that we index through v-arrow data, the pointer to the heap block. Let's look at both. Get is one line. It returns v-arrow data at index. The computer finds the address as base plus I times the size of one int. That is one add, one multiply, and one read. Set is just as short. It writes x into v-arrow data at index I. It overwrites one live slot. The size of the array does not change. So both get and set are big, O of 1. Each is one address computation and one read or one write. Growing the buffer never touches these. Only append and insert can move the block. Inserting inside the array is the shift from Chapter 2. Every later element has to move one slot. The one new thing is that insert may first have to grow the buffer. Let's walk through it. Insert starts by calling append. This makes sure there is room, and it grows the buffer if it is full. If append fails, we return -1 and stop. Now this loop shifts the tail one slot to the right. It starts at the last element and moves down toward index I. Each element steps over by one to open a hole. When the hole is open, we drop x into v-arrow data at index. The new value is now in the middle, in the right place. Delete is the same shift the other way. There is no growth this time. We just close the gap left by the removed value. This loop shifts the tail one slot to the left. Each element moves down by one, starting at index I and moving toward the end. Then we subtract 1 from v-arrow size. The array is now one shorter, and the gap is gone. Let's sum up the cost. Insert and delete inside the vector are Chapter 2's shift unchanged. Every later element moves one slot. The one new thing is that insert may first have to grow by calling append. Both live only in C, where the shift loop is the mechanism. So insert and delete in the middle are both big O of n. In the worst case, we shift up to n elements. It is only big O of 1 at the very end of the array, where nothing needs to move. Let's run the full API and trace it. This is the driver program. It appends 4 values, overwrites one with set, reads one with get, inserts in the middle, deletes from the front, and frees at the end. On the next slide, we build one row per call. Here is the trace. One row per call, and the glowing cell shows what that call changed. We start with an empty vector, size 0, capacity 0. Append 10. The vector holds 10. The size is 1. The capacity grows from 0 to 1. Append 20. Size is 2. The capacity doubles from 1 to 2. Append 30. Size is 3. The capacity doubles from 2 to 4. Append 40. It fits in the spare room, so the capacity stays at 4. Only the vector and the size change. We pick up after the 4 appends. The vector holds 10, 20, 30, 40. Size is 4 and capacity is 4. Set index 1 to 99. Only the vector changes. The size and capacity stay the same. Get index 2 returns 30. This is a read. Nothing in the vector changes. Insert 55 at index 1. The buffer was full, so this insert grows the block. The capacity doubles from 4 to 8 and the size is 5. Delete index 0. The rest shift left. The size drops to 4 and the capacity stays at 8 because deleting does not shrink the block. The trace is the same every run. It shows values, sizes, and capacities only, never a raw address. And there is one heap block, so one free.